All right, in this section we're going to learn about, or relearn about, I guess, the basic logarithmic form for integration. This is one that we've learned about in our first calculus course, and it basically goes like this. The integral of du over u is equal to ln of absolute u plus a constant. So the way I think about this is that if I'm integrating a function and it looks like it has the form of a fraction where what's on top is the derivative of what's on the bottom, that is the logarithmic form, and its integral is the natural log of the absolute value of u. We need the absolute values to make sure that the domains match up, because of course in this fraction u can be negative. There's nothing wrong with having a negative in a fraction, but the logarithmic function, we have to plug in positives, so we have to put the absolute value on that article. This rule patches the hole that we have in the general power formula, so you might recall that the integral of u to the n du, the power rule for integration, is we increase the power by 1 and divide by the new power plus a constant. And this is true as long as the power is not equal to -1, right? Because if the power is -1, then this formula would have you dividing by 0, which obviously we can't do. So we're going to do some examples here. In this case, we're trying to see, does our function fit the logarithmic form? And if so, what substitution do we need to make in order for that to happen? So if we look at this function in part A, if this fits the logarithmic form, then the only way that happens is if u is equal to 2x minus 1. Now if u is 2x minus 1, then its derivative is 2. So du is 2 dx. And I want 2 dx on top. And right now all I have is dx, right? This factor of dx on the end is like having a dx on top. So I want a factor of 2. And I can throw 1 in because it's a constant. I'm just going to compensate outside. So now I've got 1/2 times the integral. This stuff here, that's du. And of course on the bottom is u. So this is du over u. And the integral of du over u is ln of absolute u. So we get 1/2 ln absolute u plus a constant. And now we're going to put our x's back in. 1/2 ln of absolute 2x minus 1 plus a constant. Alright, let's try another. Take a look at this one. Probably right off you're thinking, well, this isn't a log rule, because the derivative, if it were a log rule, you're thinking, okay, then u would have to be x squared plus 1, and certainly the derivative of x squared plus 1 is not x squared plus x plus 1, and you're absolutely right when you think that. But we need to do a little bit of work to rewrite this, because right now there's not a whole lot we have. The way it's written right now doesn't fit any form. But let's just note that this is sort of an improper fraction, in that an improper fraction of polynomials, because the degree on top is equal to the degree on the bottom. If the degree of a polynomial on top is greater than or equal to the degree on the bottom, we can do some division. And so that's what we're going to do first to rewrite this. I'm going to take my x squared plus x plus 1. I'm going to divide it by x squared plus 1. And so here's a little refresher on polynomial long division. I'm going to ask myself, I'm looking at just the first terms, what do I multiply by x squared to get x squared? That is, of course, 1. And now I'm going to take this 1 and I'm going to multiply it. I'm going to distribute, right? So multiply by the whole divisor. That's x squared plus 1. And I'm going to have to subtract the whole thing. So x squared minus x squared is nothing. Then we bring down the x, and 1 minus 1 is nothing. So when I do the subtraction, I just get x. Now we're done. This is a very short polynomial division problem. You're done when the degree of the polynomial at the bottom here is less than the degree of your divisor. So there's degree 1 on the bottom. We have a degree 2 there. And so how we interpret this result now is that we can rewrite this fraction. This fraction is equal to 1, that's our quotient, plus, and then you put your remainder, in this case x, over your divisor. 1 plus x over x squared plus 1. And you could check, if you did some algebra to add, to get a common denominator and add these together, you would recover the original fraction they gave us. So now I have two terms, and I can split up an integral over addition. So I've got the integral of 1 dx plus the integral of x over x squared plus 1. We know how to integrate 1, so I'm not going to worry about that right now. This other one here, I'll note that I've got a x squared in the bottom and just a plain old x on top. So I think this could fit that logarithmic form. If we let u equal x squared plus 1, then its derivative is 2x. So du is 2x dx. And I almost have du up top. I just need a factor of 2. I'm going to throw in the 2. I'm going to compensate with a 1/2 out here. Now I've got the integral of 1 dx plus 1/2 integral du over u. Now I can go ahead and integrate the whole thing. The integral of 1 is x, and then I have 1/2 times the integral of du over u. Well, that's ln of absolute u plus a constant, and now we're going to put the x's back in. Now, when I put the x's back in, we don't actually need the absolute values in this case, because x squared plus 1 is already always positive. You could include the absolute values. It's not incorrect to write the absolute values. They're just not necessary. And there's our integral. Okay, let's try another one. In this example, I can see that I do have an x squared. I've got x plus 1 squared, right? So that's obviously a quadratic in the bottom. And I have 2x on top. So it seems like it could be something that fits a log rule. It doesn't fit it exactly right now. But let's see what happens. If u is equal to x plus 1, then there's two things that we get. One, certainly du is just 1 dx. So du is dx. But also we'll note that we could take this equation and rearrange it to get an expression for x in terms of u. So x is u minus 1. And that's helpful to keep in mind when you're making substitutions. Sometimes it can help to get an expression for x to plug in if the u substitution doesn't jump out entirely, if how everything substitutes is not obvious. This can be a helpful step here. So I'm going to use that now. I'm going to use these substitutions. 2x is 2 times u minus 1. On the bottom we have x plus 1 squared, and that is u squared, and dx is du. Now we kind of have an algebraic path forward here. I'm going to take this factor of 2 outside the integral. And this u squared in the bottom, I'm going to write that as a u to the minus 2, a factor of u to the minus 2 outside. But here's, I just want us to observe kind of what making the substitution has done. It's given us an algebraic path forward because now I can distribute that u to the negative 2. And that wasn't really much of an option up here when we had it written with x's. So when I distribute that u to the minus 2, I have u to the minus 1 minus u to the minus 2 du. I'm going to rewrite this. I've got 1 over u minus u to the minus 2. It might seem odd that I've kept the negative exponent in one term and not in the other, but it's because of the integral forms. So the next thing I'm going to do is split up this integral, because these are two different types of integral forms. I'm going to split up the integral over subtraction, and when I do that, I have to make sure that each of those integrals has that factor of 2 that's sitting outside this whole integral. So I got 2 times the integral. Now 1 over u du, another way to write that is du over u minus 2 times the integral u to the minus 2 du. This first one is obviously, now we can see, a log form. The second one is a power rule. So that's why I wrote the second term still with a negative exponent. So I got 2 ln of absolute u minus 2 times, now when we apply the power rule here, I'm going to increase the power by 1, so that's a negative 1 power, divide by the new power, and now I have plus a constant. And we're going to simplify. So I got 2 ln absolute x plus 1. Now this next term is going to be a plus 2 over x plus 1. That u to the minus 1 here, I threw that back down in the bottom, plus a constant. There is our integral. Okay, so here's another one. Now they're telling us this is a log rule here, and it might not seem that obvious. Basically, you know, what we're going to observe, and it's something we've already observed, but only after rewriting an integral, maybe doing some algebra or making a substitution, often only after doing that can we see what form it is. You know, we're trying to get the integral to reveal its form to us. So I'm going to rewrite this in what's going to seem like an awkward way algebraically, but it's going to help us. So instead of 1 over x ln x, I'm going to bring this factor of x up and write it as a 1 over x up top. So I've got 1 over x dx up top over ln x. And you might already see what substitution we're going to make and how it's going to work out. I'm going to try letting u equal ln x. And if u is equal to ln x, then du is 1 over x dx. So look, that's precisely what we have here. There's our du, there's our u. So this is the integral of du over u. And this is ln of absolute u plus a constant. And putting our x's back in, we've got ln of absolute ln x plus a constant. All right, we got one more now. This one also says use substitution with the log rule. So I'll just say, you know, I think it's good to take a look at this, size it up, and I think observe that it doesn't immediately seem like a log rule, you know, like a logarithmic form. I have a square root of x in the bottom, and it's not really clear how I have something of the form with a function and its derivative sitting on top. The substitution we're going to make here that will be helpful is we're going to let u equal the square root of x. And if u is equal to the square root of x, then u squared is equal to x. And I'm going to differentiate this function to get my du and dx. So taking the derivative with respect to x, we have 2u du is equal to dx. Okay, so what we have now is 2u du on top, or 2u, and I'm going to put the du at the end. On the bottom, what we have is u plus 1. Okay, now looking at this, still not looking at something that looks like a function with its derivative sitting on top, but maybe if we think back to what we did 2 or 3 examples ago, we could say, oh, this is an improper fraction. I've got polynomials and the degree on top is equal to the degree on the bottom, we can do some division. So I'm going to take 2u, I'm going to divide it by u plus 1. So what do I multiply by u to get 2u? Of course, that's 2. Now I'm going to multiply 2 by the whole divisor here, distribute, so I get 2u plus 2. I'm going to subtract the whole thing, and then I get negative 2. Again, we're done. This is just one iteration of this process we need. And we interpret this, means this fraction, 2u over u plus 1, is 2 minus 2 over u plus 1 du. Now we can split up this integral of 2 du minus, and I'm going to pull this factor of 2 outside of the second integral. So I have 2 integral du over u plus 1. Now, some people would look at this second integral, and first of all, we can, I think, recognize it as fitting a log form. Some people might want to make a second substitution and say, let's let v equal u plus 1, so we have dv over v, and it very explicitly fits that form. I think we could see clearly that what's on top is exactly the derivative of what's on the bottom. So I'm going to skip making that second substitution. I'm going to integrate the whole thing. So this first one, the integral of 2 du is 2u. And then we have minus 2 times ln of absolute u plus 1 plus a constant. And now we can plug in our x's back. So this is 2 root x minus 2 ln absolute root x plus 1. And here's another case where if we want, we can actually drop the absolute values, because root x, when we write root x like this, we mean the principal root, the positive root. So root x plus 1 is positive. So whether you use the absolute values or not, either way is just fine.